Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Masato Matsuoka and Takeru Suzuki with us today. Hello, Masato, and hello, Takeru.
Hi, Frank.
Hello there. Masato, let's start with you. What is your geolocation? Where are you located at?
Now I'm located at Gifu Prefecture in Japan.
Very cool. Very cool. And Takeru, where are you at?
So now I'm in Tokyo, and Tokyo is 200 kilometers east of Masato's place.
Okay.
So Gifu is in the center part of Japan. Tokyo is located in the eastern part of Japan.
Nice.
So separated.
One fine day, I will visit Japan. It is on my bit bucket of places to visit.
Oh,
world. Looking forward to it one day.
Yeah, please. Yeah.
Thank you. Yeah. Let's see, it is summer in the Northern Hemisphere. So how is summer in Japan? Is it hot? Is it humid?
Yes, it's very humid and hot. The high temperature here in Tokyo is around between 35 and 40 degrees Celsius.
Wow.
So it's over 100 degrees Fahrenheit. Maybe.
Yeah, yeah. Wow, that's hotter than I had imagined. Wow. So it is August 5th of 2024 as we record this, and I'm in Phoenix, and it's up into the 41, 42, 43 C. We get quite hot in the summer, but not quite as humid. It's all very good. Let's see. And Masato, let's start with you. What do you like to do for research?
In this paper, I conducted a numerical simulation of solar wind, but actually now I'm at another lab and studying the wave particle interaction in the laboratory plasma.
Oh, very cool. Very nice. Very nice. And Takeru, what do you like to do for research?
Okay, I started my research around 20 or 30 years ago, and my first PhD thesis was on solar wind.
Oh,
and after that, I worked on plasma astrophysics, like red giant winds or protoplanetary disks. Yes, so many things related to MHD or plasma astrophysics.
Very cool.
Particularly focusing on winds or streams. Yes.
Very nice. Very cool. And that is going to bring us to this very lovely APJ article. Bring that up, and it is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Effect of magnetic diffusion in the chromosphere on the solar wind. And Masato and Takeru, take us away.
Okay, so I like to cover introduction part. The main message of this paper is that magnetic diffusion is very important in the solar atmosphere, or the atmosphere. So recently, solar wind have been observed frequently and also measured in situ, for example, by Parker solar probe.
Yes.
But the driving mechanism of the solar wind is still uncertain. And many people, including I, believe that the alpha waves or alphanic waves is one of the promising mechanisms in driving the solar wind. So in my case, I've worked on this subject in the last 20 or 25 years, and but so far we didn't include any effect of magnetic diffusion, or in other words, we did our research or simulations or theoretical model with ideal MHD approximation.
Okay.
So ideal MHD approximation. Meaning of ideal MHD is that the magnetic field and the background gas are fully coupled.
Yes.
But this is this may be, this assumption may be broken in the lower atmosphere of the sun or even cooler states.
Okay.
Because the ionization is not sufficient. For example, the temperature of the photosphere or the chromosphere on the sun is several thousand Kelvin.
Yes.
The ionization degree there is less than 1. So please go to figure 2.
Figure 2. Let's head down to figure 2.
Yeah.
Okay.
We like to skip figure 1.
That's okay. All good. Figure 2.
Yeah.
Ionization fractions.
Yeah.
Yes.
It's already our output of a simulation, but please take a look at the top panel. The vertical axis shows the ionization degree.
Yes.
And horizontal axis is the distance from the photosphere.
Okay, so going in. Okay.
Yeah. And in the upper layer, you can see that the ionization degree is around 1. That means that gas is fully ionized.
This is deeper. Yes.
Yeah.
Goes...
The temperature is high. But in the lower part, you can see ionization degree is less than 10 to minus 4. And
yes.
Okay, so the ionization is quite weak.
Okay, cool.
Yeah. Yeah.
Yes, and do you want to describe the different colors of the curves here a little bit?
Okay, so we are calculating 4 cases. The blue case, so blue dashed dot line shows the result of the ideal MHD approximation. So it's a kind of classical setup.
Yes, yes, okay.
Yeah. The other 3 lines include different types of magnetic diffusion. So OD stands for ohmic diffusion.
Okay. Okay.
Yeah, in this case, electrons are the source of the magnetic field because the magnetic field is created by the current.
Okay.
If you recall Ampere's law.
Yes.
And in this case, electrons are colliding with background neutral particles if the ionization is not sufficient. Then the motion of electrons or electric currents are inhibited, which reduces the magnetic field.
Okay, I'm with you. Yes.
Yeah, and AD stands for ambipolar diffusion.
Okay.
This is more effective where the density is lower. In such circumstances, the magnetic field coupled with charged particles drifting from the bulk of neutral component.
Yes.
So neutral and magnetic plus charged particles are behaving in a different way.
Yes.
So M1 includes the OD, ohmic diffusion, and M2 include ambipole diffusion, and M3 include both.
Nice, very nice.
Yes, and ionization degree looks very similar, but bottom panel is also very important one. So in this bottom panel, we are showing magnetic Reynolds number. So what is magnetic Reynolds number? So this is the ratio of inertial term over diffusion term.
Yes.
If this is huge, the effect of magnetic diffusion is negligible.
Correct. Yes. Okay.
So in green case, the value is kind of huge.
Yeah.
Ohmic diffusion is not so important in the entire atmosphere.
Okay. Okay.
But in the orange and red solid cases, in cases, ambipole diffusion is included.
Yes.
Value is less than 10 or nearly almost
unity. Yeah, almost unity.
And if this magnetic Reynolds number is less than, say, 100, the effect of ambipole diffusion should be included.
Yes, very good.
Ambipole diffusion plays an important role in the thermodynamics of stellar or solar atmosphere.
Okay, and you've got you have 3 diamonds here, and what are the diamonds?
Okay, this stands for the location of the top of the chromosphere. So that is
Okay.
defined for the temperature equals to 20,000 Kelvin, if
Okay.
I remember correctly.
Okay.
Masato, is it
Temperature markers.
correct?
Yeah, that's true.
Okay.
Okay, cool. Good. I'm with you. Thank you.
Yeah. So below these diamonds, the gas is in the chromospheric condition. Yes.
Okay, good. I'm with you. Yes. Temperature marks.
Yes. And could you go back to the section 1 again? So
Sure.
based on this ionization discussion, actually, many previous works have worked on the role of magnetic diffusion in the chromosphere of the sun. Yes, these works. Yes. But so far, there are almost no work searching for the effect of magnetic diffusion in the chromosphere on the upper layer.
Yes.
In the wind region.
Yes.
So that is the purpose of our paper.
Cool. Very clear. Very clear. Okay, I'm with you.
Yes.
Awesome. Yeah.
And maybe from this point, I like to pass the baton to Masato. Is it okay? You can briefly introduce the setup and quickly go to the results section.
Okay, great. I'm with you.
Okay. So I move on to the section 2 methods. We perform the non-ideal simulations to reproduce the solar wind streaming out from the superradially open flux tube.
Yes. Okay.
The flux tube model is described in section 2.1. And the first equation is the expansion factor which corresponds to the cross section.
Yes.
And within this model, we set a fixed perpendicular parallel magnetic field.
Yes. Okay.
Yeah.
Good.
So on this flux tube model, we solve a full set of MHD equations. The basic equations listed from sections equation 3 to equation 7.
Okay, let's take a look at that. And those look like some conservation equations. Very good.
Yeah, so
yes.
And equations we solve basic equations including gravitational force or radiative cooling.
Good. Okay.
Thermal convection and phenomenological galvanic turbulence in equation 7 or equation 5.
Yes. Okay.
And finally, of course, we included magnetic diffusion. This term is yes.
Go ahead.
Okay, so in this one-dimensional regime, the ohmic diffusion and ambipolar diffusion works in the same way.
Okay.
And below of these equations, we explain some basic setups of these equations and the meaning of each symbols.
Good. Ideal gas. Okay.
Yes. So ideal gas law and the eta is mean diffusivity.
Yes.
And the value of conductive heating.
Conduction. Yes. Okay. Sure.
Right. And next is radiation.
Is the flux big conductive flux? Yes. Radiation. Here we go. There's our cooling. Okay. Good.
Yeah. And the important thing of radiative cooling is in thin plasma optically thin plasma, such as corona and solar wind, the radiative cooling has positive dependence on density.
Yes.
This point is important in the following our analysis.
Okay, I will keep that in mind. It's usually, yeah, in the low density, it's rho squared. So there's an important factor of rho there.
Yeah. And the next equations are phenomenological Arvinic turbulence.
Yes.
To handle the accretion of waves within a one-dimensional regime.
And
these terms are written by Elzessa variables. Equation 19.
Z plus and minus is okay, good.
Okay.
These are the Essler. Yes.
And next we move on section 2.3.
Okay.
The non-ideal.
Non-ideal.
Yeah, this is the part we included for the first time in this simulation. And in this section we explain how to evaluate the effect of the diffusion numerically using some equations.
So we got ohmic, and then we got the ambipolar. Okay, there's our ionization fraction. Two densities, ions and rho n neutrals. Okay, good. I'm with you.
Okay, so this evaluation is based on the ionization fraction and mainly ionization fraction. So in the below part, we describe how to calculate the ionization fraction in equation 24, 25, and 26.
Okay, let me get a sense of that. 23 x's. Sure. Okay, good. 24, 25, 26. Now that we got that, then you can get the ratio. Yes. 24. What is W, gal? What is W?
W gal means written in the below of equation 25, and this is
okay.
Yeah.
Okay. Yeah.
Galactic ionization.
Yes.
From the interstellar radiation.
Okay.
Yeah. So below 25, equation 25, interstellar radiation field.
Yes. Well, yeah. Okay. I'm good. I'm with you. Okay.
Okay. Here we skip some section 2.4 and move on 2.5.
Conditions, numerical methods. Yes. Initial conditions, I should say. Boundary and initial.
Yeah. In the initial condition, we the four models Takeru-san mentioned before.
Yes.
Are calculated from the same initial condition.
Good.
It's cool and static temperature.
Yes. Start hydrostatic. Boop, boop, boop. Okay. Very good.
Okay, and I'd like to pass the baton to Takeru-san to explain the section 2.6.
Okay.
Okay, so yeah, actually we developed our own code since 2000, maybe 4 or 5.
Yay.
Initially ideametric equation. And the point is that we cover we numerically and dynamically solve the wave propagation directly. Yes. Particularly the propagation of alphanic or alphan waves and compressive waves, including sound waves. So without any approximation. So in order to do that, we have to resolve one wavelength, at least by 4 or maybe 10 mesh points.
Hopefully, yeah.
Yeah. So nowadays it's not so computationally expensive, because of the development of computer, and also our geometry is 1D, so it's very simple. So the point is, we can directly solve wave propagation and dissipation of aphanic waves. And dissipation of aphanic waves leads to the heating of the surrounding media.
Okay, yes.
So the new point is, as Masato mentioned, the effect of non-ideal MHD is included. That will reduce, or that will dissipate the propagating alpha waves.
That's
But
good.
so the dissipation of alphanic waves leads to the heating. So
Yes.
yes, no-MHD effect enhances the heating, but reduces the propagating alphanic waves from the surface.
Good, good. I'm with you.
And figure 1 shows that initially static and static density distribution, and particularly above 10 to minus 2 on the horizontal axis, the density increases by 100 times.
Yes, it does.
This is because of the mass supply from the chromospheric region.
Okay, okay.
Initially, we didn't assume any high temperature corona, but after some time, the upper layer is heated up, and that high temperature region, from that high temperature region, downward thermal conductive flux heats up the cooler chromosphere.
To an equilibrium, yes.
Yeah. Then the cooler chromospheric gas is evaporating to the upper layer, which is called chromospheric evaporation.
Yes, okay.
By that mass supply, density increases in the upper layer. Yes.
Very good.
Yes.
Good.
And in this panel, we are only showing density distribution, but in figure 3, we are showing different physical variables. So from this figure 3, I like to pass my baton to Masato. This is the main result.
Nice.
Okay, thank you.
Yes.
So this figure 3 shows the radial profile of a temperature, the top panel,
Yes.
and the density, the middle, and the bottom is the radial velocity.
Yes.
And the line style and color are the same as figure 2.
Yes. Okay, good.
So, and the diamond means the same altitude, the top of the chromosphere.
Yes. That mark. Okay.
And now we focus on the temperature and density profile
Okay.
to explain the effect of magnetic diffusion.
Okay.
Yeah, at first, when we see the temperature this profile, in the chromosphere, when the ambipolar diffusion is included, the temperature in the chromosphere is slightly higher.
Yes.
And in the lower corona, the region between 10 to minus 2 and 10 to minus 1
Yes.
is slightly lower when ambipolar diffusion is effective.
Yeah. Okay. Good.
And these are the direct result of magnetic diffusion in the chromosphere. And
Yes.
when the aphanic MHD waves are damped by ambipolar diffusion in the chromosphere, the diffusion turns the magnetic energy into heat.
Yes. Okay.
So the chromosphere is slightly heated up, and eventually the magnetic energy reaching the corona is suppressed.
Good. Yes, I'm with you.
So the temperature in the atmosphere in the corona is less heated to make the decreased temperature.
Okay. Yes.
Yeah, and next we refer to the change of altitude of the transition region
Okay.
in the temperature.
Yes. Yes. Okay. Good.
And
Sure.
when bipolar diffusion is included, the altitude of transition region is increased. This is because suppressed photospheric evaporation, Takeru-san mentioned before.
Yes.
And by this decreased coronal temperature and increased chromospheric temperature, the difference of temperature reduced, and so it results in the reduction of thermal conduction.
Right. Yes.
So the suppressed thermal conduction means the suppressed chromospheric evaporation, and this leads to higher altitude of transition region.
Yeah, moves up. Okay. Good.
And next we move.
Yes. Yes.
Yeah, and the difference of the altitude of diamond directly means the change of altitude of transition region.
Yes, I'm with you. Yes.
And we next move on the density profile.
Okay. Yep.
Yeah, the density drops in the chromosphere and in the corner and outer region when ideal and just ohmic diffusion case
Yes.
has a larger density than that of the ambipolar diffusion cases.
Yes. Who's here? Yes.
Yeah, this is related to the less suppressed coronal heating. So when the ambipolar diffusion is included, the gas were not transported enough.
Less. Yes.
It makes this density profile.
Good. Okay.
And the density profile, interestingly, this decreased density profile makes the convergence of the temperature in the outer region.
Yes.
Yeah, as I mentioned before, that less density means less radiative cooling.
Yes, which goes as rho.
Yeah, so even though when the ambipolar diffusion works, the coronal heating is suppressed, but
Yeah.
the radiative cooling is also suppressed.
Yes.
So in the outer region, the temperature profile became at the same level as the ideal case.
Yeah. Yes.
Yeah. In this figure, the important thing is that magnetic diffusion works only below the chromosphere.
Yeah.
So below this diamond.
Or so, yeah.
However, the difference due to magnetic diffusion appears in the upper region.
Correct. I'm with you. Yes.
Yeah, this is an interesting point of our numerical simulation.
Beautiful. Beautiful. Okay. Yes.
Next, we move on to section 3.3.
Very clear. Good. Okay, section, whoops, let me go get back here. Section 3.3, energetics. Yes.
Yeah, this section is in this section we give a detailed explanation of why this the wind structures in figure 3 was made.
Right. Good.
But here I would like to explain the energetics using table 1.
Sure.
Which
let's see, one sec. Yeah, in table 1, do 6 kilometers. Okay, I'm good. Table 1, let's go to, did I miss it? Table 1, table 1, table 1.
Table 1 is the previous page.
Yes, sorry.
Okay, thank you.
I'll get there.
Yeah. Okay, so we wrote the model. And the last two models are the case with including both of magnetic diffusions.
Yes.
But larger amplitude or at the amplitude of fluctuation at the photosphere.
Okay, yeah, that gets easy.
I will refer to these two models in maybe next section. Okay. So now we focus on the 4 models.
And it's okay. Cool.
And each column means energy fluxes. Before the energy fluxes, the third column.
Yes.
Means that column means velocity fluctuation at the photosphere, and this corresponds to the input energy.
Yeah. Okay.
Okay. So.
Yeah. Okay.
These values which have a capital L means luminosity or energy flux of each type of several types of energy.
Okay.
Subscript A means galvanic luminosity.
Okay.
Or Pauling flux. And the subscript K means kinetic energy.
Yes. Okay.
And L is radiative cooling.
Yes. Okay.
And G is gravitational flux.
Okay. Yes. Forgot about that one.
Okay, now when we look at this LATC.
Okay.
So and when we compare the value of LATC of M0 and M3.
Okay, 8 to 3.
The value of M3 is about 3 or 4 times smaller.
Yes.
Since this subscript TC means top of the chromosphere.
Okay.
So the difference of LATC means that less energy are injected into the corona.
Nice. Very good.
This is the direct reason of why the lower coronal temperature decreased.
Yes. I'm with you.
And in this table we and the
Mass rate. You can explain about mass rate.
Okay, thank you.
M dot.
So now we have a mass loss rate.
Yep.
And mass loss rate corresponds to output mass, and when the value of mass loss rate decreased about 6 or 7 times.
Yeah. Yes. Order of magnitude. Yes.
And this mass loss the M, but this muscle rate and decrease was recovered by
Yes.
augmenting the fluctuation at the photosphere, the delta V0.
Yeah. Okay. Makes sense.
Now we look at take a look at M3 149.
Right. We get 2 extra models here.
And in this model, the amplitude of the velocity fluctuation is 1.49 kilometer per second,
Okay.
which is about 1.2 times larger than that of previous cases.
Yes. And then we got an M3 170, which is even a little bit larger.
Yeah, so, and the mass loss rate of M3 149 is about the same level of
As M0.
Yeah, ideal case.
And
And we investigated the detailed dependence of mass loss rate in figure 8.
Figure 8. Let's go to figure 8. So 6, 7, and 2. Very nice. Okay. Dependence of M dot. Here we go. There we are. Okay. Yeah.
So in the horizontal axis of figure 8 is the delta V0. And the vertical axis is respectively the top panel is mass loss rate. And
Yeah.
the bottom panel is each galvanic fluxes.
Ooh,
and
good.
kinetic flux.
Oh, good. Okay.
So now we focus on top panel.
Yeah.
When the delta V0 is 1.49, the mass loss rate is the same level as ideal case, and
Yes.
when we increase the amplitude, the mass loss rate becomes larger and larger.
Looks linear.
This is it. However, the ratio of axes is different. In
Okay.
In the ideal case and the no-ideal case, which has the same mass loss rate, the difference between a difference of delta V0 is just 1.2 times.
Right.
However, the
Okay.
when we see the value of ideal and non-ideal case of the same delta V0,
Yes.
the value of non-ideal case is 6 or 7 times smaller.
Okay. Yeah.
Which means that when we increase
Yeah.
when we increase the input energy a little bit,
Yes.
and we acquire a huge difference in the output value, mass loss rate.
Yes. That makes yes.
Yeah, and this figure clearly shows the nonlinearity of the wave.
Good. I'm with you.
And maybe Takeru-san, could you explain the physical reasoning of this nonlinearity?
Yeah, I like traditionally explain the top panel of this figure.
Okay.
So yeah, please focus on red points.
Yes.
And the leftmost part, the injected energy is a delta V perturbation is 1.25 kilonewton per second. And the rightmost part, the input perturbation is 1.7 kilonewton per second.
Yes.
If you take the square of delta V naught,
Okay.
that is proportional to the injected energy.
Energy.
So the difference between the leftmost case and the rightmost case is about twice difference in the energy injection.
Yeah. Okay. Sure. Yes. I'm with you.
But if you take a look at the vertical axis, Masa's rate is different by 10 times.
Yes.
So that is nonlinear behavior Masato explained.
Got it. Got
Yeah.
it. Okay.
Yeah, if you increase the injection twice, the output increases 10 times.
Yeah. Okay. That was my bad. Okay.
It's very strange. So what happens? This is because of the reflection of the aphanic waves in the atmosphere.
Okay.
In the leftmost case, only point few percent of the input energy is going to the kinetic energy of the final solar wind. Yes, and in the leftmost case, the most of the energy is go to the reflected component of the alpha waves.
Okay.
Yes. Actually, this is already known by theoretical modelers for solar wind. So the energy efficiency is only 1% or even less. The efficiency means the final kinetic energy divided by the injection energy.
Okay.
Yes. And more than 90% of the injected energy go into the reflection.
Okay.
Yes.
That increases as you
In
go.
the rightmost part, the efficiency increases to around few percent. But still, the dominant component is the reflected component.
Yes.
Yes. Nearly 90% of the injected energy is going to the incoming alpha waves.
Okay.
Yeah, that are reflected somewhere in the atmosphere. Some of them are reflected in the chromosphere. Others are reflected in the corona.
Okay. Thank you.
Yes, that is the physical reasoning of this nonlinear behavior of the Masa's rate as a function of the input energy from the photosphere.
Gotcha. Thank you.
Yes. Then we like to we like to introduce the final figure, which is figure 11. A little bit about the comparison with the observation.
Ooh,
So
that's
but will be explained by Masato again.
Okay.
Yes.
Yeah, and this is this figure. Vertical axis of this figure is normalized density fluctuation. Horizontal axis is the same as previous figures.
Yes.
And in this figure, the blue solid line and red solid line are our simulation results, and the others are the observational values.
Ooh, good. Okay. Okay.
And in this simulation models have the same mass loss rate, which is the same level as observational value.
Yeah. Yeah. Cool.
Yeah. When we look at the lower corner region, the density fluctuation of non-ideal MHD case decreased compared to the ideal MHD case.
Yes. Okay.
And this reduction stems from the nature of ambipolar diffusion.
Okay. Yeah.
Since ambipolar diffusion selectively dumps the higher frequency wave than lower frequency wave.
Okay.
So in this region, the higher frequency waves are preferably damped, so the density fluctuation decreased. And this characteristic is preferable to explain the observational data.
Okay, good.
So in terms of the density fluctuation, the non-ideal MHD effects is worth considering.
Indeed.
Yeah, and this is the final result of our paper. And next, Takeru-san, could you move on the discussion and summary?
Very nice. Very nice. I like this figure. Very good. Okay.
Okay, thank you. I like to mention this figure.
Okay.
Yes, in the outer part, you may think that our theoretical result, simulation result, and observation are inconsistent because most of the observation data are below these two lines in the
Yeah.
outer region, above 1 or 10 solar radii.
Okay.
Yes,
Mm-hmm.
but this is natural because these observations are from the interplanetary scintillation measurement.
Yeah.
So then the positive and negative density fluctuations are canceled out along the line of sight. So therefore, these data points should be taken as a kind of lower limit.
Yeah, lower bound. Yeah. Mm-hmm.
Lower bound.
Mm-hmm.
So these data points could be larger than these values if we can measure one particular point.
Yes.
So
So in essence, good. Right?
yes. Okay, and yeah, this is final remark on this figure, and we like to move on to the summary and discussion.
Okay.
So yeah, in this paper, we only focused on the solar atmosphere and solar wind.
Yes.
But magnetic diffusion will be more important in cooler stars,
Yes.
like M-type stars, main sequence stars, or red giants.
Yeah. Okay. Mm-hmm. Yes.
Because the temperature in the atmosphere is lower, therefore ionization degree is lower.
Yes.
Then the neutral component plays a more important role in the thermodynamics
Yes.
of the atmosphere.
Yes. Mm-hmm.
So therefore, we are now planning to extend our model to red giants or red dwarfs.
Ooh, very good. Nice. Okay.
And also, with respect to the treatment of our simulation, that is related to section 4.4, I think.
Low mass.
Yeah, lower. Oh, okay, so this is the lower mass main sequence star.
Right.
Sorry, the treatment is related to section 4.3, probably.
Okay. Non-equilibrium.
Yeah,
Mm-hmm.
and the ionizations are
Right.
calculated by assuming the equilibrium.
Yes.
And that is not so good, particularly in the less dense region. For
Yeah.
example, upper chromosphere.
Yeah.
In that region, probably non-equilibrium effect should be taken into account. Yes. And also, in our treatment, we are assuming one fluid MHD with magnetic diffusion.
Mm-hmm.
Probably two fluid, so the neutral and charged components required to treat upper layer because density is lower there.
Right. Right.
Yeah, and neutral and charged components behave very differently.
Indeed.
So multi-field treatment will be more important, and we are now planning to that.
Cool.
Yes.
Very good. Nice.
So yeah, this is our final comment. So I think we are done for our article. Yeah, we have some appendix.
Oh yeah. Yeah.
Yeah, pointing to the detailed treatment of the magnetic diffusion. So that will be important in more realistic 3D treatment.
Right.
Yeah, but I think it's too much in detail. So
we'll
I
just
think
note that it's there. Very good.
yeah. So I think we are done for our article.
Very cool.
Yeah, thank you very much for interview.
Yeah, beautiful work.
Yeah.
Beautiful work. Masato and Takeru, thank you so much for walking us through your very beautiful article. Nice. And you touched on it a little bit there toward the end of, going in new directions. So let me just push on that a little bit. And so where do you think we go given the published article? Are there any plans to go to multi-D? How about a 2D or a 3D? Is there plans for people doing additional data points, maybe with the Parker Solar Probe or something else? And so just sort of next steps, where do we go?
Okay. In the context of the solar physics, yeah, multi-D treatment is important in order to directly compare with in situ measurement or remote observation of the upper chromosphere or lower corona, which is related to figure 11 we showed. Yes. But I also personally think that the extension to M dwarfs, N-type stars or red giants,
very interesting.
Yeah, important.
Yeah.
So M-type stars are kind of fancy object, because that is the central object of exoplanets.
Yes.
Yeah, like space weather of exoplanets. That is one of the direction of our extension of this project.
Cool.
So, yes. So yeah, we are planning to do both directions. But of course, I think we need time. But please stay tuned.
Indeed, these things do take time and energy. So very cool, very cool. Well, it'll be very exciting to see this develop over the next couple of years. It'll be very nice. I'm looking forward to it.
Thank you.
Yeah. All right. Masato, Takeru, thank you so much once again.
Thank you very much.
And that will do. Thank you. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.